Okay, so it's very nice to call me a physicist. I haven't done physics in a long time. I'm another that elbowed my way into cognitive neuroscience. So yeah, so my talk has no equations, so just be warned. I'm very sorry. This is the relaxed talk. Okay, so my talk is titled The Development of Dynamic Network Modes Supporting Attentional Flexibility. So to walk you through each part of that title, attentional flexibility, that is the ability to shift our attention from one thing to another based on changes in the external environment and internal goals. So for example, you're all hopefully, after that rest, attending to me right now, but maybe your phone vibrates, so you shift your attention to your phone to check how important it is. Maybe it's spam email, so you decide to shift your attention back to me. Now that's just an example, but we're doing this all the time, and it's essential for complex adaptive behavior in humans. Now, children, they undergo rapid development in this ability to shift their attention. And how this manifests is when we do attentional flexibility tasks, they will have, so older children will have faster reaction times and generally lower accuracies. Now, children with attention deficit hyperactive disorder, or ADHD, and that represents around 8% of the pediatric population, these have issues with attentional flexibility, often causing both social and academic difficulties. And when we do tasks, the same sort of attentional flexibility tasks with these, they will generally exhibit slower reaction times and lower accuracies. So now, how do we look at the brain activity that underlies both the normative development of attentional flexibility, but also the impairment in ADHD? What better way than MEG, magnetoencephalography? Now, MEG puts us in a unique position where we have good spatial resolution and also excellent temporal resolution. So we can reconstruct estimates of source level estimates of neural activity with millisecond temporal precision. Now, the issue is that the data can become very high dimensional very fast. So we generally care about these three primary dimensions. So we have region. We can sample any region in the brain as densely as we want. We have frequency. So do we care about 1 Hertz oscillations? Do we care about 100 Hertz oscillations or something in between? And then we have time, of course. Now, what we generally do to reduce those dimensions a bit is we pick sort of a frequency or a region or a time of interest. So maybe we pick a region of interest and we look at the time frequency progression, or we could pick a frequency or time of interest and look at the spatial distribution of activity. Now, this is great. This represents a really robust approach to mega-analysis. However, when we're looking at development, we actually expect there to be really large, dramatic changes in neural activity to occur during that period of time. And so we're clearly going to add biases by picking a particular canonical frequency range or maybe a time of interest. So how do we solve this problem? Well, luckily, the guys at Oxford University, who I've collaborated with before, they created a method, many methods actually, but one called dynamic network modes, or Dynamo. And this is a machine learning data-driven approach where we take the source level MEG data, then we find a latent description of this MEG data, and we call these latent modes. So that is my personal definition of modes. And these will each contain a unique kind of fingerprint of spectral and spatial characteristics. And then what we can do is we can take those latents and look at the way that they evolve over time. So at each time point, the model enforces that, that all of the modes must add up to 1, but then the mixture of those modes will change continuously through time. So then we simply analyze those lower dimensional, more compact dynamics rather than the original MEG data. So the benefits of this are manifold. So firstly, it's data-driven. So we actually learn directly from the data. We don't do kind of biologically informed or anything like that. And we don't have to epoch. We don't have to do any time frequency decomposition. It's compact. So here's just a few figures from the Oxford group that created this model. And they've shown several times that you can have as little as 6 modes, and that can explain both resting and task-based data. And also we can do baseline free analysis. And I spent my whole PhD trying to say how baselining was terrible. And so this is excellent. I don't really have time to explain that right now. So the data set that we analyzed was collected by Margot Taylor's lab at SickKids and also the POND network. So we looked at 67 children and adolescents aged 4 to 19 years, so really spanning that key developmental window for attentional flexibility. 32 of these were diagnosed with ADHD. and they performed an attention shifting task. So bear with me here. So we're all going to do it. So what they would see is a screen like this, and what they're trying to do is see which of these top shapes matches the bottom shape in either its color or its shape. So here, clearly the left matches because that's a pentagon and this is a pentagon. So they would click the left button. The next trial, it's again the left that matches. Again, it's pentagons. Now here, it's now the right shape that matches, and we're looking at triangles rather than pentagons. So we've performed a small attention shift, and we call that an implicit shift because we're still matching shape, we're not matching another dimension. But now this trial, this time, we're looking at color rather than shape. So we've actually switched the feature, the type of feature that we're looking at. And we call this an explicit shift. And these are going to be harder. So both of these conditions are going to be harder to perform, but particularly this explicit shift requires the biggest kind of change in your attention. And this is very simple, but this task was designed to be suitable for very young children. So firstly, we analyzed the behavior of the participants. So how did they respond in terms of reaction times and accuracy? And we found that greater cognitive shifts led to slower reaction times and lower accuracies. So this just shows that the task works. So the explicit condition here, they have the slowest reaction times and the lowest accuracies. So we also found, again, expected that older children did better at the task. They had faster reaction times and higher accuracies. Now, interestingly, we saw no significant effects of ADHD. And bear that in mind because for one of the results later. And this is just for our cohort. So maybe if we had a higher N, we would have done. But yeah, there is a trending of the means you can see so that the children with ADHD had slightly slower reaction times, but it was not significant here. So now the dynamo part, so the fun part. So we inferred 6 modes, just like the Oxford group had done before, directly from the continuous source level MEG data. And these are the modes that we inferred. And these actually really closely resemble the modes, both spectrally and spatially, that the Oxford group have inferred from task and rest data with adults. So what this suggests is that maybe these are like a canonical set of network modes that we can infer from MEG data, a bit like resting state functional MRI networks. So following that mode inference, we looked at their dynamics. We epochhed those around trial onsets, and this is what the kind of average response of those modes looks like. So that's where the trial is, it begins, and we can see there's this reshuffling of modes. And I just want to highlight 3 of these modes in more detail. So this frontal mode, which increases following trial onset, and these 2 posterior modes that decrease following trial onset. So this frontal theta mode, so this reflects increased frontal theta power and connectivity. And the important thing here is that we didn't have to do any time frequency decomposition to infer this mode and its dynamics. We do post hoc spectral analysis, and I'll explain that in more detail if anybody wants at the end. And then when we look at the dynamics of this mode, we see that it responds, so it increases following trial onset to a greater degree in the explicit and implicit shift conditions. So clearly, this frontal theta mode is related to that process of attention shifting. Now we wanted to look at how this mode develops. So it does develop with age very nicely, linearly. So if you take all of the activity over all time of this mode, kind of representing how much does it contribute to brain activity overall, this increases with age. And that's across both controls and those with ADHD. And you can actually look at the dynamics compared directly between the older and younger children, so separated around 12 years old here. And you see that actually there is a distinctly different profile in the way that they respond to the task compared to the younger children. And when we compare the children, the controls with those with ADHD, the children with ADHD had lower overall activity. And this is despite no behavioral differences. So actually, this mode description of the data is better at distinguishing the children with ADHD compared to their behavior. And interestingly, we've now replicated these findings. So this was the first study that we did on it, but now we've replicated them within Margot Taylor's lab. So here's a few figures from Liam Bailey, who's here, I think. So he found exactly the same mode and actually found that it increases with age in that cohort as well. And that was with 92 neurotypical controls and a different task as well. And then Kareem Mathani from my lab, he's found the same mode again, and also found that it differentiates controls from children with neurodevelopmental disorders. So what we think from this is we may have derived this generalizable marker of cognitive development. So now the posterior modes. Firstly, we have this one, which is strongest around primary visual regions, and it has a strong alpha peak. And this will look familiar to hopefully most people in the room. And if we look at the dynamics of this mode, it decreases. So it does the opposite thing compared to the frontal theta mode. So where there's a stronger decrease in activity in the shift conditions compared to the non-shift. And so we think this reflects the very well-studied alpha event-related desynchronization, which has also been shown in the literature to relate to the amount of cognitive load in attention tasks. But the interesting thing here is that we didn't have to apply a canonical frequency range here. We actually identified this activity in an entirely frequency agnostic way. And we actually expect the alpha peak frequency to change across this developmental range. So it's really important that we have these approaches. Next, we have this other posterior mode, which is also strong around the primary visual regions, but also the supporting and higher order visual regions. And it has a lower frequency profile, so extending to theta and delta. And if we look at this, although it does desynchronize a bit like this mode, I think the interesting part is these two bumps, which seem to capture the progression of the visual evoked response from primary visual regions, which occurs around 100 milliseconds, to higher order visual regions, which occurs slightly later in the trial. And if we zoom in on this mode a little bit more, we find that it has the opposite effect with age. So actually it decreases in its relative contribution to brain activity in the older children compared to the younger children. So how do we summarize all of these findings? Well, firstly, we have created a dynamic network model of attention shifts. So when you shift your attention, just like from me to your phone, perhaps, maybe your frontal theta mode is increasing in activity and your posterior alpha mode is decreasing in activity. And we've also created a dynamic network model of development. So here is a line representing development over childhood. And when you're at the bottom of this line and you perform this task, your response is dominated by that posterior visual drive, like that bottom-up drive. And then when you age, you are dominated more by this frontal theta, perhaps top-down control mode. So what we've done is, using no real prior assumptions about the nature of the data, we have inferred these spatial and spectral modes of brain activity, and we've seen how they evolve with time in a behaviorally relevant way. Now, the question is, we've now replicated this across several data sets, but are all cognitive functions well described by the interplay of these same 6 or so canonical spectral modes? And that's an invitation. So if anyone has MEG data lying around, I can send you pipelines. Okay, so thank you very much. I'll be happy to answer any questions.